Hello viewers, this is Jeyapradha, Department of Computer Applications, SFR College. Today I am going to discuss about elements of transport protocol. Transport protocol provides a mechanism for applications to communicate with each other without interacting with the internet protocol layer. Let's see the elements of transport protocol one by one. Elements of transport protocol. The transport service is implemented by a transport protocol between the two transport entities. Like the transport protocol resembles exactly like the data link protocols, but the main difference between these are the working environment in which the two protocols operate. At the data link layer, two routers communicate directly via a physical channel, whether wired or wireless. Whereas the transport layer, this physical channel is replaced by the entire network, which have been represented in the diagram. Another difference is the process of establishing a connection over the wire is simple because the other end is always there. Even on wireless links, the process is not much different. Just to send a message is sufficient to have it reach all the destinations. If the message is not acknowledged due to an error, it can be resent. But in the transport layer, initial connection establishment is complicated one. Also, the transport layer is the potential existence of storage capacity in the network. One more difference is buffering and flow control are needed in both layers, but the presence in the transport layer of a large varying number of connections with fluctuations in bandwidth. Let's see the main elements of transport protocols like addressing, connection establishment, connection release, error control and flow control, multiplexing and crash recovery. First one, addressing. Consider the situation, a user process wishes to set up a connection to a remote application process. It must specify which one to connect. For that, we define transport addresses to which processes can listen for connection request. In the internet, these endpoints are called ports. This regards we use some generic terms called TSAP, that means Transport Service Access Point, that can be used to define a specific endpoint in the transport layer. The analog endpoints in the network layer are called NSAP, Network Service Access Points. IP addresses is an example for NSAPs. Let's see the relationship between the NSAP, the TSAP and the transport connection. Application processes can attach themselves to a local TSAP to establish a connection to a remote TSAP. These connections can run through NSAP on each host. The purpose of TSAP is each computer has a single NSAP, so some way is need to distribute multiple transport endpoints that can share the NSAP. The represented diagram displays a possible scenario for a transport connection. Consider this scenario. First of all, a main server processes attaches itself to TSAP 1522 on host 2 to wait for an incoming call. How a process attaches itself to a TSAP, it's outside the networking model and depends entirely on the local operating system. Second step, an application process on host 1 wants to send an email message, so it attaches itself to TSAP 1208 and issues a connect request. The request specifies TSAP 1208 on host 1 as the source and TSAP 1522 on host 2 as the destination. This action results in a transport connection being established between the application process and the server. Third step, the application process sends over the mail message. Fourth step, the mail server responds to say that it will deliver the message. Finally, the transport connection is released. Next one. While stable TSP addresses work for a small number of key services that never change user process, so we often want to talk to other user process which cannot have TSAP address that are known in advance, or they may exist only for a short duration. To handle the situation, an alternate scheme can be used. That scheme name is port mapper. In this model, when a new service is created, it must register itself with the port mapper, giving both its service name and its TSAP. The port mapper records this information in its internal database so that when queries come in later, it will know the answers. Many of the server processes that can exist on a machine will be used only rare. It is wasteful to have each of them active and listening to the stable TCP address all day along. To handle this with the initial connection protocol. Let's see about second element of transport protocol, that is connection establishment. Establishing a connection is an easy but it is a tricky one. At first it would seem sufficient for one transport entity. It just to send a connection request segment to the destination and wait for a connection accepted reply. The problem occurs when the network can lose, delay, corrupt or duplicate packets. This behavior causes serious complications. Rather than allowing packets to live forever within the network, we devise a mechanism to kill off aged packets that are still hobbling about. With this restriction, the problem becomes somewhat more manageable. Packet lifetime can be restricted to a known maximum using the techniques like restricted network design, putting a hop counter in each packet or time stamping each packet. The restricted network design includes any method that prevents packet from looping combined with some way of bounding delay, including congestion over the long possible path. It is difficult given that internets may range from a single city to international in scope. The second method, that means putting a hop counter in each packet, consists of having the hop count initialized to some approximate value and decremented each time the packet is forwarded. The network protocol simply discards any packets whose hop counters become 0. The third method, timestamp each packet, requires each packet to bear the time it was created, with the routers agreeing to discard any packet older than some agreed upon time. This method requires the router clocks to be synchronized, which itself it is a non-trivial task, and in practice a hop counter is a close enough approximation to age. Next one, we do not normally remember sequence numbers across connections of the destination. We still have no way of knowing if a connection request segment containing an initial sequence number is a duplicate of a recent connection. This knack does not exist during a connection because the sliding window protocol does remember the current sequence number. To solve this specific problem, Tomlinson introduced the three-way handshake. So, the given diagram explains the possible three scenarios of a three-way handshake. The normal setup procedure when host 1 initiates the first one, host 1 chooses a sequence number as X and sends a connection request segment containing it to host 2. Host 2 replies with an acknowledgement segment acknowledging X and announcing its own initial sequence number as Y. Finally, host 1 acknowledges host 2 choice of an initial sequence number in the first data segment that it sends. In a B figure, the first segment is a delayed duplicate connection request from the old connection. So, this segment arrives at host 2 without host 1's knowledge. Host 2 reacts to this segment by sending host 1 an acknowledgement segment, in effect asking for verification that host 1 was indeed trying to set up a new connection. When host 1 rejects host 2 attempts to establish the connection, host 2 realizes that it was tricked by a delayed duplicate and abandons the connection. In this way, a delayed duplicate does not damage the connections. The C diagram explains the worst case of the three-way handshake when both a delayed connection request and an acknowledge are floating around in the subnet. Third one, connection release. Releasing a connection is either than establishing one. There are two styles of terminating a connection, that is asymmetric release and symmetric release. Asymmetric release is the way the telephone system works. When one party hangs up, the connection is broken. Asymmetric release is abrupt and may result in data loss. But symmetric release treats the connection as two separate unidirectional connections and requires each one to be released separately. Symmetric release does the job when each process has a fixed amount of data to send and clearly knows when it has sent it. Unfortunately, this protocol does not always work. There is a famous problem that illustrates this issue. It is called two army problems. The given diagram represents the 4 protocol scenario for releasing a connections. Fourth element is an error control and flow control. In connection establishment and release, we face two key issues are error control and flow control. Error control is ensuring that the data is delivered with the desired level of reliability, usually that all of the data is delivered without any errors. Flow control is keeping a fast transmitter from overrunning a slow receiver. So, previous is the problem 1. The solution to the above issues are a frame carrier and error detecting code like checksum CRC that is used to check if the information was correctly received, or a frame carries a sequence number to identify itself and is retransmitted by the sender until it receives an acknowledgement of successful receipt from the receiver. This technique is called ARQ, that means automatic repeat request. Third one is there is a maximum number of frames that the sender will allow to be outstanding at any time, pausing if the receiver is not acknowledging frames quickly. If this maximum is one packet, the protocol is called stop and wait. Larger windows enable pipelining and improve performance on fast and long links. Last one is the sliding window protocol. This combines these features and is used to support bidirectional data transfers. Fifth element in the transport protocol is multiplexing. So, multiplexing or sharing several conversations over connections, virtual circuits, physical links that can play a vital role in several layers of the network architecture. For example, if only one network address is available on a host, all transport connections on that machine have to use it. When a segment comes in some way, it is needed to tell which process to give it. This situation is called multiplexing. If a user needs more bandwidth or more reliability than one of the network parts can provide, a way out is to have a connection that distributes the traffic among multiple network parts on a round robin basis. So, this method is called inverse multiplexing. Example for inverse multiplexing is SCTP, Stream Control Transmission Protocol. The given diagram demonstrates the multiplexing and inverse multiplexing concept. The last one element is a crash recovery. So, crash recovery, if host and routers are subject to crashes or connections or long lived recovery from these crashes become an issue. If the transport entity is entirely within the host, recovery from network and router crashes is straightforward one. To illustrate the difficulty, let us assume that one host, the client, is send a long file to another host. The file server using a simple stop and wait protocol, the transport layer on the server just passes the incoming segment to the transport user one by one. Partway through in transmission, the server crashes academically. When it comes back up, its tables are reinitialized, so it no longer knows previously where it was. In an attempt to recover its previous status, the server might send a broadcast segment to all other hosts announcing that it had just crashed and requested that its client inform it of the status for all open connections. Thank you for watching, viewers. Let's see in another video.